candies allocated to K children, Leetcode daily. We're giving an this problem before starting is literally the same problem as Coco eating bananas. It's just a slight twist to it, but it's literally the same. Okay, so it's an array candies. Each element in the array is a pile of candies. You cannot merge two piles together. You can only divide this into subpiles. So the 5 can be a 3 and a 1, a 4 and a 4 and a 1, a 3 and a 2, etc. You're giving an integer k. You should allocate piles of candies to k children. So just each child has to get the same number of candies. Each child can be allocated candies from one pile of candies. So basically, this 5, a kid can take 3, and you cannot take from any other pile. Return the maximum number of candies each child can possibly get. So when solving a question like this, binary search is the most efficient way. If you solve Coco eating bananas, as I said before, you'd be able to solve this, I think. The idea here is you'd have like a line of candies from 1 to like the maximum number of candies here, which is 8. So basically no child can get more than 8 because a child can only take from one pile, essentially. And you're going to tell me, like, how is he going to get the 8? How is he going to get to 8? Well, basically if k is 1, right, the maximum is going to be 8, right? So yeah, you're gonna have to do like from 1 to the maximum number of candies he can take, because depending on the k, it can be d8 actually. And the idea here is, from all these candies, the idea is to find a number where it actually validates the part where you can you're not gonna have to merge piles together. So basically, let's say we have from 1 to 8, we found like 4. The idea here is to go through each candy, right, and check how many 4s can you make out of these piles. So for this one you can make 1 4, for this one you can make 2, for this one you can make 1, right? And scrap the remainders. So that means we got 4 here. So 4 4s is good because 4 is greater than 3. That means that there's children that can take there's 3 children that can take 4 candies. There's gonna be some unused, obviously, but then when this is valid, you're gonna say, okay, we tried 4, it works. How about to go and see 5? How about to go and see 5? Maybe 5 is better. So it's binary search basically. Maybe 5 can work. So we go see 5. Here 5 gives us 1, 5 gives us 2, 5 gives us 3, which is the requirement. Basically, it is the requirement. But it's higher than 4 and it is the requirement. So that's why we return 5. If you try 6 doesn't work here. It gives us 1 here and it gives us 2 here. So basically we just have 2. So the idea, as I said, is to validate every single candy I choose. So in this code here, we start from 1 to the maximum number of candies, right? And it's a binary search. We get the middle, right? And then we just invoke this can work thing. Can work is candy per kid, basically. And it just counts the number of kids that can take that number of candies. So we loop over them, we start dividing, we're seeing, like, let's say it's a 4, here we can get a 1, here we can get 2, and here we can get 3. So sorry, 2 here, 3 here, 4 here. So basically 4. If 4 is greater than 3, then that means it's true. So basically, yes, we can actually give 3 kids 4 candies here. What we do here then is we move the L upwards. That means, okay, check a higher number, maybe a higher number works. Else we return else we bring back the R, because that means we went above, and that means it didn't work, basically. Maybe because the number is too high. So yeah, for example, if you try 7, for example, 7 doesn't work here, it gives us 1 here, so yeah, it doesn't work. Yeah, so that's basically it. And then we return L minus 1, because if you know how binary search works, it's like gonna stop somewhere and then the R goes below it. It's just if you tried it with a simple term, you're gonna return L minus 1. Just draw it out, right? Time complexity is log n for the binary search, but it's n for the iteration for every binary search. So it's n log n essentially. Yeah. So that's been it, guys. Thank you for watching. See you in the next one.